wanted to work through an example that involves the electrical field of a point charge or electrical field of point charges, and also the principle of superposition, that the total electrical field of a collection of point charges is the sum, the vector sum of the individual electrical fields of those individual charges. So in this particular problem, we're asked to picture two charges on the x-axis. So one of the charges is Q1, and it's minus 2.5 microcoulombs. The other of the charges, Q2, it's 6 microcoulombs. And they're located on the x-axis with a separation of 1 meter. And the question is, at what point on the x-axis is the electrical field 0? i.e., at what point on the x-axis does the electrical field of charge number 1 get cancelled exactly by the electrical field of charge number 2 to produce a 0 total net electrical field? So we've got to find that point. I'm going to take 2 steps in finding that point. The first step is more of a qualitative step. I'm going to kind of reason whether that point is to the right of the 2 charges, left of the 2 charges, or in between the 2 charges. And then once I know the answer to that qualitative question of what region the fields cancel, I'm going to figure out exactly the location where the field of charge 1 and the field of charge 2 are exactly, precisely equal and opposite. So I've divided the x-axis up into 3 regions. To the right of the charge number 2 is one region. To the left of charge number 1 is another region. And in between is the third region. And we'll walk from the right through to the left, just asking the question, in each of those regions, is it possible, feasible, that the 2 electrical fields could cancel out? If the electrical fields are going to cancel out, it means that the electrical fields have to be oppositely directed, and it means that the electrical fields have to be same-sized. So are those conditions possible? So let's start over here in the this region on the far right. So the electrical field points away from a positive charge and towards a negative charge. So the electrical field for E1 would be towards the left. The electrical field for E2 would be towards the right. So in this region, the 2 electrical fields of the 2 charges, which have opposite signs, are in opposite directions. So from that perspective, they could cancel out. But we are closer to the larger charge. We are further from the smaller size charge. And so it will always be that E2 is bigger than E1. We can never arrange that E1 is the same size as E2 in this region. And so for that reason, that E2 is always bigger than E1, we can't cancel the 2 fields in the region on the right. So that won't work. What about the region in the center? In this region in the center, let's again first think about the directions of the electrical fields. So the electrical field of charge number 1, which is negative, is towards the negative charge. And the electrical field of charge number 2 is away from the electrical charge. So in this region, both fields are actually in the same direction. They're both pointing towards the left, because towards the left is towards the negative charge, away from the positive charge. So in this case, the two fields can't cancel out because they're simply in the same direction. So this doesn't work either. What about in the third region, over here on the far left? So in this region, if we think about the directions of the electrical fields again, the electrical field due to charge number 1, that's towards the right because it's towards the negative charge. The electrical field of charge number 2, that's away from charge number 2, so it's towards the left. So they can cancel for that reason. They're in opposite directions. And also they can cancel in this region because we're closer to charge number 1, which is the weaker charge. We're further from charge number 2, which is the stronger charge. So we can compensate for charge 1's weakness or charge 2's strength by being closer to charge 1, further from charge 2. So there is a special point somewhere in this region where the two electrical fields are oppositely directed, equal in size. And so now we've got the mathematical task of finding that. So to find the location where the two fields are equal and opposite, E1, E2 are equal and opposite, let's start with the basic idea that the strength of E1 and the size of E2 must be equal at this location. So when I'm referring to E1 here, E2 here, I'm not thinking about the directions. The directions I know are equal and opposite. I'm thinking just about the strengths. The size of E1 is the size of E2. They're the same. Now I'm going to fill in the law, based on Coulomb's law, for the strength of the electrical field due to an electrical charge. In terms of the charge and the distance from the charge. So for Q1, I'm going to introduce a variable x, a distance x. Let me draw it on the sketch. And this is the distance x from Q1 to the location of what I call the field point, where the two fields are equal and opposite. It's at a distance x from Q1. That means it's actually at a distance x plus 1 meter from Q2. So with that introduction of that variable, let's write down what E1 and E2 are. So E1 is Coulomb constant times the charge. I'm referring here to the magnitude of the charge divided by the square of the distance from the charge, x squared. And for E2, its strength is the Coulomb constant times the magnitude of the charge, again, Q2, divided by the square of the distance from this charge. And that's not x, that's x plus 1 meter squared. So this is now a relationship between the charges, which we know, and this distance that we want to find out. So this is an equation that we now have to go and solve mathematically. You can see it simplifies a bit because the Coulomb constants cancel out. And now we're going to start the sort of more mathematical, more algebra-based process of solving this equation, given that we know Q1, Q2, for the value of x. So the first thing that I did was take x squared from the bottom of the left-hand side to the top of the right, and x plus 1 squared from the bottom of the right-hand side to the top of the left, to get these factors out of the denominators. And then I took the square root to get rid of the x squared, just replace it with an x, the x plus 1 squared, replace it with an x. So let's go ahead and do that. I'll write down the equation that I got. Here it is. So over here on the left is the x plus 1. I lifted up to the top of the left. Over here on the right is the x that I lifted from the bottom of the left to the right. And you see I've taken the square root. So I've got x plus 1 rather than x plus 1 squared, x rather than x squared. And I've got the square root of q2 over q1. I left q2 on the right. I pulled q1 over to the left. So I can rearrange this equation now as an equation for x. What I would do is group together on one side of the equal sign the terms involving an x, group together on the other side of the equal sign the terms that don't involve an x, and then I can write the equation just for x. When you do that, you get the following equation. And in this equation for x, we've got x on the left-hand side, and we've got a function of the two charges. It's 1 over 1 minus the square root of the ratio of the charges on the right-hand side. And so I can plug in Q2 is 6 microcoulombs. Q1 is its size. These refer to its size as 2.5 microcoulombs. So this is the square root of 6 divided by 2.5. If I do this calculation, the number that I get is 1.82 meters. And so that's the distance of this field point from the position of the first charge at which the two fields cancel. So I really haven't drawn this picture to scale in light of this result. This x is 1.8 meters roughly, and this distance to the right-hand charge, that's 2.8 meters. And that's the solution to the problem. If you wanted to check the problem, check your solution, you could calculate E1 and E2 based on our equation for these fields, Coulomb constant times the charge divided by x squared or divided by x plus 1 squared. And if you do that calculation, I did it, but I'm not going to write it out. I found that whether I calculated E1 or whether I calculated E2, I did get the same sized electric field. It was about 6.79 times 10 to the 3, and that's newtons per coulomb. Anyway, that's an example illustration of working with the electrical field of point charges, of superimposing electrical fields of point charges, and using those two notions, concepts, to solve this particular problem of where the electrical field vanishes due to these opposite sign, different size charges.